We're now in the Raman spectroscopy laboratory. This is rather unique for a corrosion lab. However, they do appear in some well-equipped laboratories. The utility of the Raman corrosion process is it lets us study corrosion in situ. That means that we can study the corrosion products and what's happening on the surface while it's underwater. That's rather unique. Almost all other analytic techniques that are used to study the surface chemistry of a corroding process require a hard vacuum, say scanning electron microscopy or EDS or X-ray diffraction. Obviously, when you take something that's been corroding underwater and you dry it out and put it in a vacuum, you've radically changed that surface. And your surface products are not going to be the same any longer. Now, those methods do have a place. However, studying the corrosion process while it's happening in the electrolyte is something that's really, really useful, because you can actually identify with Raman spectroscopy the chemical species that are on that surface. And that's, of course, important for us because, as we've said several times, the module works by reactivating the zinc on the surface. And the need for that comes about from the fact that zinc passivates. In other words, it builds a layer that makes it passive, and it's not able to sacrifice itself any longer to protect the steel. And so with a Raman spectrometer, we can actually identify the zinc oxide or zinc hydroxide or whatever film is on that surface, and we can also then watch its thickness change over time with this intensity of the Raman spectrometer signal. Now, the way that the Raman spectrometer identifies a molecule on the surface of a piece of metal is rather clever. And what you do is you shine laser light of a very, very fixed narrow frequency from a laser source, which is over here to my right, and you look at the light reflected from that surface. Now, most of that light is at the exact same color as the light that came from the laser. Some of that light that was shifted to longer wavelengths, and some of it is shifted to shorter wavelengths. Now, that shift of the light is caused by the light interacting with the molecule on that surface. And all molecules have a characteristic shift. And so if you look at the reflected light that is shifted, in our case we're looking at the light shifted towards the longer wavelengths. If you look at that spectrum of the light from that surface, you can actually determine the optical signature of that material or the molecule that's on the surface. So it's a very clever way of finding out what kind of molecules are on a surface while the steel or zinc or whatever is corroding. It takes quite a lot to do that. It takes a very expensive laser system, and in our case we're doing what's called confocal Raman spectroscopy. And that's the optics that extend from the lens in front of that clear acrylic block over there to my left to the lens going into the spectrograph. And so that's how the light is delivered, and then the shifted light is sent to the spectrograph. The spectrograph is not in your vision at this point, but it's a large box that contains a diffraction grating and some mirrors and some lenses and a CCD camera where the spectrum of the reflected light is recorded. And that's recorded, as I said, with a CCD camera that's connected to a computer where we record the images. Now, the other thing that we want to do in here is we want to control the growth of, say, a zinc oxide layer and then study it with Raman spectroscopy. And the way that we do that is we use a potentiostat. Now, this potentiostat then is connected to a corrosion cell, which is that clear acrylic block. And so we can very precisely control the corrosion conditions of the sample in the corrosion cell with the potentiostat. At the same time, we can deliver light in through a window in the front of that acrylic block, excite the surface that we're interested in studying, say steel, galvanized steel, zinc, or whatever, aluminum, and look at the reflected light and look at the corrosion products and exactly determine the molecules that are on that surface. Now, the potentiostat doesn't tell us the molecules that are on a surface. It just lets us control the corrosion conditions. The Raman spectrometer, however, will let us actually identify the molecules that are on that surface. And that gives us tremendous insight into the corrosion reduction process, which we discussed earlier.